So in this video of chapter number 13, surface areas and volumes, we're going to now start with another interesting three-dimensional solid figure, and it is called as right circular cone. So I'm going to remove this. Okay. So here first let us try to focus on what is a right circular cone, or how a right circular cone comes into a formation. So to understand it, here I have an interesting diagram. So focus on this diagram. Let me try to zoom in. So here we have a right angle triangle. So I'm going to just highlight it. So we have this right angle triangle. Okay. So this is our right angle triangle. We all know right angle triangle as a geometrical figure, very popular and a very useful geometrical figure. Now, if we take this right angle triangle, okay, and if we rotate it, okay, if we revolve it or rotate it 360-degree around this vertex, okay, then what we get entirely is called as a right circular cone. So a very common example of this shape of cone is nothing but the ice cream cone. We have all seen ice cream cone in our day-to-day life. It is exactly of this shape. Okay. Now, how this cone is formed is something which this diagram explains. We basically take a right angle triangle like this and we simply rotate it around this vertex, okay, at this top. And once this one complete rotation is done, whatever area is mapped into the space, that is called as a right circular cone. Okay, this thing, right circular cone. So this is how a cone is formed by using a right angle triangle. So here I have a simple diagrammatic representation of a cone. Now we are going to map the important parameters in this cone, and the first one is the radius. So this thing, okay, this circle that is formed at the base, this is called as this will be the base of our cone. Okay, this will be the base of our cone, which is circular in shape, and this will be our radius. So I'm just going to write here r. So radius, okay, r, this is called as the radius. Now we know that this was a right angle triangle, so this was its height. Okay, so once again let me mark this important parameter. So this is called as the height of our cone, and we are going to name it h. So h is the height of the cone and r is the radius of the cone. Now this slanted portion of the cone from its vertex to the circle at the base, okay, this entire thing, let me use a highlighter because it's a very important parameter. This entire thing is called as a slant height. So I'm just going to, okay, this is called as a slant height. So it is a height, but it is not like a vertical height like this one, okay, because this height is vertical and it has this 90-degree right angle triangle. But this is a slant height of the cone, and its letter is L, small l. Okay, we represent it by small l. So overall in this cone, in any right circular cone, okay, these are the three parameters which will define the whole shape of the cone. First is the radius, quite simple, this circular base which will have a radius. Then this is the height, okay, the height is from the center of this circle to this vertex of the cone. So this is like our perpendicular straight height, vertical height. And then we have a slant height, okay, this tilted slant height, which is called L. So if you note, if you focus on this right angle triangle, or even if you come to this figure, this right angle triangle, the slant height is nothing but the hypotenuse of the right angle triangle. Okay, very important. So this slant height is nothing but the hypotenuse of this right angle triangle. Okay, so these are the three parameters h, l, and r of any right circular cone. Now there is a relationship between these three parameters. So we want to see the relationship between r and l, and even h will also come into picture. Okay, so the relationship is very simple and straightforward. In fact, you can guess it. We are going to use the Pythagoras theorem, okay, to establish a relationship between h and r and l. Why can we use a Pythagoras theorem? Simply because this is a right angle triangle. So in every right angle triangle, the Pythagoras theorem is applicable. So the relationship between r and l is going to be something like this: r square plus h square is equal to l square. Simple and straightforward. It's our plain, very famous and very common Pythagoras theorem that we use in a right angle triangle. Okay, the summation of the side square is equal to the hypotenuse square. So this slant height L is our hypotenuse square. So r square plus h square, so this r square plus h square is equal to L square. This is very important in establishing a relationship between all these three parameters which define any right circular cone. Okay, so thus we have understood what a right circular cone is, and we have seen the relationship between these three parameters. Now let's move to the actual topic of this chapter, which is nothing but the curved surface area of the right circular cone. So the next topic that we are going to discuss is surface area of a right circular cone, okay, RC cone. Now once again, the formula for this is, so we don't have a proof for this formula, we just directly use a formula which is given to us. So the surface area of right circular cone is given by a formula pi into r into L, okay. So where r, we all know what is r, so this is r, I'm just going to mark here, this is our r radius, and this is L, which is the slant height. So if I give you the radius and the measure of slant height of a right circular cone, then the surface area is given by a product of pi into r into L. Quite simple and straightforward formula. Now sometimes in the problems, they will give you the value of r and they will give you the value of h. So if r and h is given to us, you can easily find L using this relationship, okay. It's basically a Pythagoras theorem. If r and h is given to us, you can easily find L. Once you know L, then you can easily find the surface area of the right circular cone. So this is a formula for finding the surface area of a right circular cone. It's a direct formula, we don't have a proof for it, we just use it as it is. Now the next topic is going to be total surface area. So let's remove this. Yes, total surface area of a right circular cone. So once again, let us first mark the parameters. So this is our r. In fact, let's use a different color. So this is r, okay, this is L, and we also have h. So this straight line here is our h, okay. R, L and h, these are the three parameters which will define any right circular cone. Now we know that total surface area of any solid figure, okay, is equal to its curved surface area plus the base plus the top or the roof of the figure. Now in this figure there is no roof, okay, because it's ending at this point, at this vertex. So we just have this base of a right circular cone. So this total surface area is going to be equal to, okay, total surface area of right circular cone is going to be equal to, so we add curved surface area, okay, plus the area of the base, Now what is the curved surface area? We just saw the formula, it's pi r L, okay, this was the formula that we used for curved surface area. So that is pi r L plus what is going to be the area of the base. Base is nothing but our normal circle, regular circle, so its area is going to be pi r square. So that is equal to, if pi r is common, so it's going to be L plus r, okay. So I'm going to box it. This is the formula for the total surface area of our right circular cone, pi r into L plus r. So always, instead of remembering the formula, because there are so many different three-dimensional solid figures that we are seeing in this chapter, no need to remember formula for any of the figures, just remember the concept. Okay, the concept is that to find the total surface area, we always do the addition of curved surface area and the area of its base, okay, and the area of its roof or the top. Now in this figure there is no roof or the top, so that is ignored and we just focus on the area of the base. So thus we have found out two important formulas for surface area and total surface area of a right circular cone, and this relationship is also very important. All these three formulas we are going to use in for solving all the unsolved problems in the next video.